Thanks, Katie. Hi, everyone. Yes, so I'm going to talk to you about a few things today related to chemodynamical modeling of external galaxies, and I'll hopefully eventually get on to talk about the initial mass function and what we learn about that from similar approaches. Mostly I'm going to be talking about work that was done by my ex-PhD student, Adriano Pocci, who's now started a postdoc in Durham without actually leaving Australia, but that is the state of the world at the moment. And there's also a number of results that have been put out in collaboration with the Fornax 3D team. Okay, so I'd like to first start by thinking about the Milky Way as a galaxy. We've seen some really thought-provoking and fascinating talks the past couple of days about how the Milky Way is teaching us about galaxy formation and how to perhaps set that in context of the overall galaxy population. So here's a beautiful image constructed from the Gaia DR2, and hidden within this data is a wealth of structure and information about how galaxies form. We know, for example, by thinking about the chemistry and motions of stars, particularly the halo, we have a very active environment in the outer halo of our galaxy. There's always lots of small things falling in all the time and mostly depositing the stars in those outer parts. We can also take snapshots in our local neighborhood and sort of think about taking a slice of the solar neighborhood in the disk of our galaxy and break this up into different chemical analyses. So this is lovely work by Michael Hayden and collaborators showing this nice sequence of alpha to iron versus iron abundance, and the very nice bimodality that you see, but that bimodality is highly structured depending on where you are around and above the disk around the sun. And not only is there a chemical structure there to be understood, but there's a connection between that chemical structure and how the stars are moving. The kinematics or the chemodynamics of the system play a very important role. And I'm going to come back to this concept throughout the talk. We should be familiar with these ideas of the velocity dispersion ellipsoid. We'll be referring to, in particular, sigma z, which is referring to the sort of range of motions, if you like, in the vertical direction in the galaxy. So clearly structure there to be understood when we connect chemistry and kinematics. And there's some really exciting examples of what you can do when you do this really well. Here we're looking at the discovery of a rather important merger event in the Milky Way's history, referred to as the Gaia Enceladus and sometimes called the sausage. And this was really detected by highlighting overdensities of stars in their integral space or their integrals of motion. So breaking up the stellar motions into, in this case, angular momentum and energy, and selecting stars in this dynamical space and seeing that they actually project to interesting locations in chemistry space. And the net result of that is that, you know, in amongst this field of stars, you actually have correlated structures, their overdensities in chemistry and in their dynamics. And this, as I said, you know, harks back to a rather dramatic event in the Milky Way's history. So the question is, can we apply these kinds of techniques to external galaxies? Okay, so I'll hopefully convince you that we can at least make a start on this. And the approach we're going to use is what we're calling chemodynamical modeling with the Schwarzschild dynamical modeling method. And the way that this method works is we first start by establishing the gravitational potential. Usually this is done by describing the light of the galaxy and then converting this to mass somehow, but you can make it more complicated if you like. Then given that potential, we generate libraries of orbits that satisfy the gravitational field that they're sitting in this gravitational potential. And then we add those orbits together in the best way to fit the kinematics and this mass distribution that we've established. And that's a really important point. We can fit these models to real data. Okay, so what we've added to this technique is somehow coloring the orbits, so attaching stellar population information to those orbits and using them as building blocks to reproduce the observed properties. So I'll just give you an example here. This is wonderful MUSE data on the nearby lenticular galaxy NGC 3115. This was an empirical study that came out a little while ago, but it's just a fantastic data set to trial this kind of method. So here we're looking at velocity and dispersion fields, higher order moments, so all exquisitely resolved, and age and metallicity maps. And there's obviously structure here to be understood. So we'll start by building the dynamical model. So here we're looking at the data at the top and the model at the bottom for the velocity and dispersion fields. This is basically to convince you that the dynamical model is good. The higher order moments are also rather well fitted. And then it comes to the chemical components. So from that dynamical model, what we end up with is a distribution of weights, if you like, for these orbits or their contribution to the galaxy in what we're calling circularity space. And this is totally analogous to the energy angular momentum space that we looked at earlier. And so we can think about how the orbits are distributed in this space, and we can try to grid up this space to make the things a bit easier. But it turns out, on the right, we're trying this with 3, 22, 195, and then all orbits combined. And the question here is how many of these components, orbital components, how much freedom do we need to reproduce the age and metallicity maps that are at the bottom? And it turns out you need sort of order a couple of hundred orbital components to match that structure. So once you've got this fit, then you obviously have a wealth of information. You have the dynamical information, and you have a distribution of the orbits for the galaxy in age and metallicity space. And somehow you've got to try to make sense of this, and that's kind of encapsulated in this diagram here. And there's a lot of information shown here, but you can think of it as each panel is kind of the weight contribution in age and metallicity space. So metal rich is at the top, old is on the right-hand side. And how they're distributed on the sky is shown in these little thumbnails. So these are like slices in the age metallicity space for this galaxy. Now, also shown in line plots are values of this vertical velocity dispersion, sigma z. And the reason we picked this out is because it's a good marker for the dynamical temperature of the orbits involved. So while there's a lot here to take in, I just want to highlight a couple of key outputs from this kind of analysis. So we see that there's a fairly large presence of old but flat orbits in this galaxy, which would suggest that there's an old cold disk in there that's been well preserved. Perhaps that indicates a lack of major mergers, at least in the past 10 gig years or so for this galaxy. We also see that as the stellar population ages, the velocity dispersion is decreasing. This looks like some kind of disk cooling sequence. And we also have a population, a very diffuse population of low metallicity stars that are on hot orbits. And that is likely to do with accretion, so the accreted components, low mass galaxies and so on. So that's how we can use this kind of space. I'll just focus here on that cooling sequence of the disk. Here we're looking at that velocity dispersion in the y-axis against look-back time or age, because we have the archaeological record. And so NGC 3115 is shown in the points, the blue points, and this compared with direct measurements of high redshift galaxies that seem to follow a similar trend of higher dispersion at higher look-back times. And that potentially relates to the formation epoch, the conditions of the gas, turbulence, and so on. We heard a bit about that earlier today, but we're getting this from a direct fossil record in this galaxy. Okay, so we'd like to obviously try to apply this to more objects. And so I'll take you to the next steps, which is this Fornax 3D survey, which surveys 30 odd galaxies in the center of the Fornax cluster. So here are the objects with all the muse pointings indicated. A few facts and figures there about the survey, but basically I want to zone in on 3 galaxies that are quite comparable to NGC 3115. And that's FCC 153, 177, and 170. These are 3 rather edge-on lenticular galaxies. And that edge-on nature of them makes it a bit easier and less uncertain, let's say, to do this kind of dynamical modeling because the deep projection is better constrained. So here I'm looking at these 3 galaxies. The columns are data versus model alternating. And here we're looking at the kinematic fit of the model. And then I'll just scroll through here to the age and metallicity in subsequent rows of the data versus the model. So we're just applying the same technique and now fitting the age and metallicity maps for these 3 additional lenticular galaxies. And we can now overplot those on the same diagram as we had with NGC 3115. And we can see a fairly consistent trend here that when we go to larger ages or further look back times, that vertical velocity dispersion is higher, even in the fossil record, similar to that traced by the direct measurements. But there are some important differences. So Adriano dug into this a little bit deeper. And it's important to remember here, we're only pulling out the disk stars, but we are considering all ages and all metallicities. Now, we can also separate the ages and metallicities for those disk stars and see if this correlation or this trend stands up. So that's what we're seeing here. The lines are showing the dynamical temperature as a function of age on the left and metallicity on the right, while holding the other parameter fixed. right? So this is not marginalizing over age and metallicity alternately. And we see that that nice age trend sort of breaks down quite a bit. And instead, we're left with a fairly clear trend with metallicity. This is for FCC 153 and 170, sort of similar picture. 177, again, similar picture, and 3115 itself. It's a little rattier in this case, but it's a similar sort of scenario. That age relation tends to become a lot weaker, and instead we're left with what looks like a metallicity relation. And this is interesting because of what Sanjay Charbel was showing earlier in the meeting, and also published not that long ago, is that that's kind of what we see in the Milky Way, with the exception that the Milky Way keeps that age trend when you fix metallicity. So the trend of velocity dispersion with age metallicity, they are kind of, they're present even when you're holding the other one fixed. That doesn't seem to be the case in the galaxies that we've looked at. Now, it could be sample selection effects, it could be differences in methodology, and this, I think, really deserves a closer look and a closer like-for-like comparison. But I guess the important point here is this is the first time we've been able to do this kind of comparison of intrinsic properties and really pulling out very detailed properties of external systems in a similar way as what we would look at in the Milky Way. Okay, so what about, Richard. What was that?
2 minutes.
2 minutes. Okay, I thought I had 20 minutes on the schedule, sorry.
I'll double check, I think it was 12.
Oh, I've misread that.
I think there's a mistake in the schedule. It should
be, that would do it. Okay.
Apologies.
Okay. Then I'm not going to get to the IMF, but I will then highlight this interesting work here that's talking about getting to the assembly history of galaxies. So, as I said, we were looking at that circularity space and what that can potentially tell us. Now we can do that with simulations and then really try to associate structure in the circularity space we see today and associate that with major events in the galaxy's history. So here I've just kind of got a cartoon formation history here of a galaxy. This is taken from the illustrious simulations. And the larger panels are showing how the galaxy is at 3 sort of milestones in its lifetime and how the circularity space looks. And we can actually break that down into the accreted and the in situ formation or the origins of the stars that we're looking at. And what we find is that accretion tends to flesh out the central part of the circularity space, and the in situ is forming that cold, high angular momentum, high circularity component that can be disrupted by major mergers. So the point here is that there's information in that circularity space, and because we're now age dating the circularity space, that means that we can put a clock on the fossil version of the circularity space, and then start looking at how that circularity property has varied over time. And so this is very new work. It's just recently submitted, and we're attaching that age axis now to the collapsed circularity axis and seeing how it varies over time. And it turns out that we can actually do some interesting stuff. So in this work, we're looking here at when basically age dating the last major merger that the galaxies had based on the time resolved circularity for that object. And there's much more that we can do with this kind of approach. I think we're only just starting to scratch the surface. Okay, so I had some interesting stuff to talk about with the IMF as well that I'm really not going to get to, so I won't even try. And I think I'll leave it there and open the floor for any questions.
Thank you, Richard. Really interesting stuff. Sorry about that. I think it's a typo in the schedule. Okay, we've got a lot of questions coming through already in the Slack. Okay, so from Matt Wilkinson, if there was a merger in the past, would you expect this to increase the velocity dispersion of older stars within a galaxy? Would you expect velocity dispersion of old stars in a single galaxy is larger than the cosmic velocity dispersion?
It's a very interesting question, and I don't think we fully know the answer. And I think a lot of this will come down to degrees of, what is the actual value. That's why it was so valuable to do this small sample, and we hope to extend that in the future. For sure, major mergers will heat those cold orbits. Now, the extent to which that happens depends on the assembly history itself. I think there are pretty good limits on what we can do with just kind of gas density and turbulence at high redshift, in the same way that there are limits to what we can do with natural disk heating through interactions with GMCs and so on. Each of these things will add some temperature, let's say, to those disk orbits, and potentially in an age and chemistry dependent way, depending on when it's happened in the formation history. So I think that's, I'm basically saying it's complicated. And I think we're just starting to scratch the surface, but at least now we have a tool to kind of tackle it in this intrinsic space that I think will hopefully make it tractable.
Great, thank you. So there's a lot more questions in the Slack, and someone on the Zoom chat is asking you to say a few brief words about the IMF. So maybe you can comment on that in the Slack.
Okay, so bottom line is, let me whiz through it. So spatially resolved stuff on the IMF is just sort of opening up. But with this great muse data with Fornax, we're actually mapping it now for 30 galaxies. So it's a new paper. It's out by Ignacio Martin Navarro. He's got kind of a hybrid spectral fitting index technique. And Adriano's run this through his machinery, fitting the IMF variations in the same way as age and metallicity. And what we find is, so we break up the circularity space into like bulge, disk, and halo components. And we found sort of something a bit surprising is that the central parts in the disk of these galaxies quite similar in terms of their IMF, but that halo part, which is like a super thick disk, or it's at quite high scale heights. That's the part that seems to be, in this case, dwarf poor and distinct in its IMF. And again, we might be tracking the accreted component here and seeing the evidence of that distinct IMF that those low mass galaxies have. That's kind of the punchline.
Very cool. All right, thanks again.
All right, thanks.